Okay, so a couple class periods ago, actually the class right before the exam, we were talking about soils, and just a little bit of review. Remember, soils, when exposed to the elements, will evolve and form different zones or horizons. At the very top is the O horizon, O for organic. That's all the dead plant material that basically falls from the growing stuff above the ground onto the ground. Right below that's the A horizon, which is a mixture of ground up rock material and organic stuff. It's usually really good for growing things in, has lots of nutrients, and that's where water is held. Below that is the E horizon, which is the zone of leaching. And that's when you get water that percolates through your soils, grabs onto some of these nutrients, and carries them farther down into the soil column. Those things are usually deposited in a B layer, or zone of accumulation. It can be clay rich or carbonate rich. Underneath that is your C horizon, which is just basically ground up rock, and then the bedrock, which is R. So we have these horizons, and depending on the climate, the horizons are going to develop differently. So you need climate and you need time. So you need time for all these changes to take place. We talked about cool, wet climates like in the eastern U.S. that have nice, well-developed soil horizons. It's got a nice organic rich zone because you get lots of plant growth. You also get good A horizon because you get lots of good plant growth and organics. You get a decent E horizon because you do get a fair amount of precipitation because it's wet, and so on. And then we talked about tropics, where you get high temperatures and lots of rain. And the big difference is you get an enormous zone of leaching from all the rain. All that rainfall keeps percolating through your soil, grabs all those nutrients, pulls it away, and you get that really thick zone of leaching, which is essentially a dead zone for plants. They're not going to send their roots down into there because they can't get the nutrients they need. So they tend to have broad, shallow root systems. So now, our third example is kind of a cold, dry climate. And what we have here in Colorado would certainly fall into this category. We're semi-arid here. We get 10 to 15 inches of rain a year. And if you look at what naturally grows around here, it's sagebrush. We don't get much for grasses. We don't get much for trees, especially out here on the prairie. You get up in the mountains, you get a little bit more precipitation. But down here on the prairie, it's cold, it's dry, nothing grows really well. So what is that going to do to our soil horizon if it's cold and if we don't get much rain? First of all, you're going to expect lots of organics in a cold, dry climate. No, you're not getting lush vegetation. So your organic zone isn't going to be all that well defined. Your A zone is the next zone. That's organics and rock. You can have much there either if you don't have much organics. What's beneath the E zone, which is zone of leaching, right? You can have much of a zone of leaching? No, because you don't have much rainfall, right? So basically, you're not going to develop soil horizons really well. So we have few organics. You have poor development of the O and A because you don't have much O. You don't have much organics. It's too dry and too cold to get lots of plant growth. And you don't get much of an E horizon. But one thing that really does happen well in cold, dry climates is you get lots of evaporation. A lot of times when the rain lands on your soil, it doesn't even soak all the way through the soil column. What happens is it sort of starts to soak down, but then the dry weather always seems to come right away, and all that soil moisture will evaporate back up into the atmosphere. So you don't get much of a zone of leaching, but the high evaporation rates tend to leave behind lots of salts in your soil. And if you've ever been out on the prairie, if you dig in the dirt, you'll find lots of whitish, powdery substances in it. And it's not drugs, it's this calcium carbonate that's left behind by evaporation. And that calcium carbonate can cement together all of those little rock and few organic particles. It acts as a cement. And you get a substance called caliche. That's the whitish salt material that binds together your soil particles. And the soil that forms from it is something called hardpan. It's really common around here. It's even more common in parts of, say, West Texas and New Mexico. In fact, the soils are so hard there that if you own a home there, you probably don't have a basement. And the reason you don't have a basement is this stuff is like concrete. An earth mover can't even dig into it. You have to blast it. And nobody wants to go through that expense. So basically they just put down a concrete pad and build a house on it. No basements at all. So that is the origin of hardpan, or caliche. In order to get clays, which you have in the B horizon, you have to have water. Since this is a dry climate, we don't have much water, so you don't get much B either. Mostly what you get is cemented together rock fragments in dirt with very few organics. So the soils tend to be thin. The horizons tend to be poorly or not developed at all. And the soils tend to be cemented together. So very few things grow well in that. Sagebrush, for some reason, loves it. It's evolved to take advantage of the poor horizon development, the high salt content, but most plants can't tolerate that. So you can see that climate, time, has a huge effect on how your soils actually develop, how fertile they'll be to grow stuff in, and how they affect people trying to build structures on them. Ours always present because that's the bedrock in the area. So any questions on kind of the thought process of how these different soils develop? So I gave you 3 different scenarios: the cold wet, the cold dry, and the warm dry, the tropics. And they all have very different looking soils. So your bottom line here in terms of what this actually looks like, it's solid rock covered by a thin layer of weathered rock with very few organics. And these things can be heavily cemented with salt from all the evaporation that you're getting in this dry climate. All right, any questions thus far? And the general name for these kinds of soils we mentioned a couple times: hardpan, caliche. I've seen it also called calcrete, which is sort of caliche and concrete mixed together. It's just really hard, difficult soil to deal with, both as a farmer because you can't plow it, and as a developer because you can't dig and put foundations in it very easy. Yeah, this kind of soil was a real bane to the travelers that settled the West 200 years ago. They came west expecting soil like they had back east. And they came out here, they couldn't plow it, they couldn't grow anything in it. So a lot of folks that came out here expecting to farm ended up being miners and loggers and looking for other lines of work, because the soils in the West in general tend to have lots of salts from these high evaporation rates. That's actually kind of what it looks like. And if you took a rock hammer and whacked it, it would sound like rock, because all that white calcium carbonate salt holding together rock fragments. You can see some small rock fragments in there. And there's very few organics because there isn't much growing on this stuff because it's really difficult for plants to send roots into this. And then once they do, they don't find a lot of the nutrients they need. So again, you typically find these in arid to semi-arid climates. There are some coastal areas that have it, especially where you have big tidal flats that go through a daily wetting and then drying. And as the salt flats, tidal flats dry out, the water evaporates and leaves the salt behind. Humans have also caused these inadvertently by activities that compact the soil to the point where water can't even infiltrate into them. So the water falls, it ponds up on the surface, and then evaporates and leaves behind a layer of salt. So these are soils that are typically too hard to plow and too hard to dig into to put foundations. But yet, at least here in the US, we have lots of places where we have these soils. Okay, so we've talked about soils now from a standpoint of how they develop, how they stratify or create these horizons, how that affects plants that grow in them. What we'll probably do with the rest of the class is talk a little about engineering, about how humans interact with soils and how the soils respond to our messing with them. Because we like to mess with them. We dig up a lot of stuff. All you have to do is drive around Greeley, Fort Collins, and all you see are rock trucks and earth movers from all the development that's going on. So our soils are always being tinkered with by humans, and they respond in certain ways when we mess with them. So in order to get to there, we have to have a basis for talking about different kinds of soils. And there's a lot of different classification schemes. It's one thing scientists love to do is classify, put different things in bins so that we don't have to talk about millions of things. We can talk about smaller numbers of groups of things. And we do that with soils. And I don't even care if you write this down because we're not going to use it. But I'll just show you that it's out there. So one of the ways that we use to classify soils is based on a taxonomy, really similar to how we group living organisms. We have mammals and reptiles and amphibians, so we have orders and suborders, and we do the same thing with soils. If you look at the little box on the left, it talks about soil orders, alphasols, ultisols, oxasols, vertisols, so on. Those are all different soil types that are closely linked to climate. And on the right is a map showing where you find these soils worldwide. So it's kind of a big scale approach to looking at soils. For our purposes, though, it doesn't tell you really anything about how it responds to humans messing with it. It basically tells you where these soils form, can you grow something in it, what parts of plants grow on it naturally, but it tracks very closely to climate. So for this class, we're talking about the environment, which has always some impact on humans, doesn't tell us much about how the soils impact humans. But there are other soil classification schemes. We're going to use two different ones in here. And in fact, this first one we're not even going to use that much, but we will talk about some of the variables used in this classification scheme and how we can use those variables to come up with reasonable assumptions on how the soils will respond to us messing with it. So this next classification scheme is more of an engineering approach. It's called the Unified Soil Classification Series. And again, I'm not going to ask you to memorize the details of this. But basically it breaks soils into three big categories. Coarse soils, where you have a lot of big fragments, and by big fragments I mean the pieces that are in your soil are bigger than sand size. And then we have fine soils, soils that are made predominantly of material that's sand size and smaller. And then a third category for those that are mostly made of organic materials. And again, I don't care if you remember the details, I just want to sort of throw these out because we will be doing a lab a little later in the semester on soils, and you're going to use something called a soil survey. These are done by county. It's basically a big book of maps and descriptions. It shows you every soil that exists everywhere in the county. And there's hundreds of different soils. And then you can go in and say, oh, here's the part of land, there's the parcel of land I'm interested in. Look at these 8 different soils. Then you can go look up things about the soils. It can tell you, oh, this is great soil to build stuff in. This is a terrible soil to build stuff in. This is a great soil to grow stuff in. This soil will only support a 2-story structure. So it's super useful in terms of how humans can interact with them. But we'll get to that with the lab. This is just kind of an introduction so that when you do the lab in a few weeks, the terms won't be totally unfamiliar to you. Okay, a couple of terms. One term that we use a lot with soils is a term called grading. And it has to do with the sizes of the particles that are in your soil. Now, if you take more geology classes, or perhaps if you've had a physical geology class in the past, there's a term that geologists love to use, and it's something called sorting. Sorting and grading are the opposite of one another. In geology, when we say something is well sorted, you can think of it as that they've sorted everything into similar sized particles. So a well sorted material will be something where all the particles are the same size. Say they're all sand sized, or they're all clay sized, or they're all gravel sized. If you pick up a shovel full of loose material and everything in there is roughly the same size, that's called well sorted. Now you could put your shovel down somewhere else and look at it, and you might find a variety of different sizes. You might have some big gravel pieces mixed in with sand pieces, mixed in with clay pieces. When you have all these different sizes present in a soil or sediment pile, that's called poorly sorted. Now for soil science, I don't know why they have to use a different term, but they do, and it's the opposite term, and it's something called grading. So a well-graded soil means that there's all different grades or sizes present. So it's the opposite of well-sorted. Well sorted, all particles are the same size. Well graded, all particles are different size. This one might require a little bit of thought, but I'll ask you a question. What do you think is stronger or more stable? A well-sorted, or excuse me, let me start that over. What do you think is more stable? A well-graded soil or a poorly graded soil? A soil where all the particles are the same size, or a soil where all the particles are different sizes? What do you think would be stronger? And why?
Poorly graded soil?
Why?
Because the weight can be dispersed throughout the same size particles.
That's a decent explanation, but think of it this way. Okay, let's say we have some big gravel pieces, okay? And let's say that's all we have are gravel pieces. And that's what it looks like, okay? Now, we talked a few weeks ago that strength is derived from touching, right? Friction. And you can see that you get these particles that are touching. There's touch there, touch there, touch there, there. So these things are touching, right? What if you added in a bunch of small particles? You would fill in the gaps, right? So you could put some really fine stuff in the little pore spaces, right? You have more touching or less touching? Now you have more. So this is what we call a well-graded soil, where you have different sizes, and these tend to be strong because you have more friction, more touching. So yeah, those small particles sort of fill in the gaps and give it more cohesion. That makes sense? So yeah, well-graded soils are highly desired when you want to build a big, heavy structure or building on it. The well-graded tend to be stronger. Why is that? More internal friction as the smaller grains fill in the pore spaces between the big grains. So right away, even the terminology starts to give us information about how these soils will respond when we mess with them, when we dig them or try to build things in them. And again, don't write this down, but it just sort of shows you the three categories. So we have organic soils here, fine-grained soils where 50% or less are basically 50% or more are sand size, and coarse soils where less than 50% are sand size. And then you can see some are well graded, some are poorly graded, and so on. So these are just terms you might run across later. We're not going to get into them much today. We'll come back to this when we do the soils lab. Okay, I don't need you to remember this either, but it's worth writing down so that you have it in your notes. Because there's a third classification scheme for soils that we will use, and we'll get to it here near the end of class. And it relies on the proportions of three different small size particles: clay, silt, and sand. You guys are all familiar with sand. You have an idea of how big sand is. Silt is slightly smaller, and then clay is even smaller yet. Basically, silt and clay are so small that with the human eye, you wouldn't be able to really tell the difference. You can either get different sieves or microscopes. Geologists are weird people. We're always sticking dirt in our mouth. And one of the reasons why is that you can tell the difference between clay and silt by biting it. If you bite it and rub it between your teeth, clay will not feel gritty at all. It'll be nice and smooth. Silt will be somewhat gritty. And you guys know what sand is, because I bet you ate sand as a kid. But yeah, geologists are a weird bunch. So clay is the super small particles, 2/1000ths of a millimeter in diameter. That is really small. Silt, 2/1000ths to 5/100ths. And sand is bigger than that. And you guys have seen sand particles. You know what it feels like. So soils can be described based on the proportion of each of these three components. And that's something we will get to. But before we get to it, this is the part of the class that I really wanted to get to today. We're going to talk about three properties that soil scientists determine for various soils that tell us a lot about how they behave. And it relates back to something we've been talking about for a couple weeks. Remember we talked about Newtonian fluids, Bingham plastics. That's actually what these properties refer to. We'll talk about how to use them and how to think about soils in terms of whether they would be good to develop on or not. But I'll let you write this down and then we'll talk about it. Okay, so this first soil property is something called the liquid limit. And you see the definition here. It's the lowest water content that a soil can have and behave as a Newtonian fluid. Okay, so let's go back. What's the difference between a Bingham plastic and a Newtonian fluid?
Bingham plastics is like hard. It doesn't go down well, but Newtonian fluids like water, it goes down.
Yeah, the Newtonian fluids don't have any strength at all. They will move whenever you stress them. Doesn't matter if it's a little stress or a lot of stress, they will move. If you want to build on soil, do you want your soil to move? No, so you do not want your soil to exceed the liquid limit, because at that point it becomes a Newtonian fluid and flows away. So let's say we have a liquid limit that equals 56. Now this is 56%. So what that means is if your water content is greater than 56%, it's going to behave as a Newtonian fluid and have no strength. If it's less than 56%, then it's going to behave as a plastic or as a solid. And it will have strength. So if you want to build on a soil, do you want a high liquid limit or low liquid limit? You want a high liquid limit because it needs to take in a lot of water before it loses its strength. If you have a liquid limit of 10%, that means that your soil can only have 10% water before it'll just basically wash away. You want something that has 70, 80, 90% for a liquid limit, so it can take in a lot of water, so that basically every time it rains it doesn't just wash away. Okay? So you want a high liquid limit. Okay? So that's the first property, liquid limit. Lowest water content that your soil can have and still behave as a fluid. Plastic limit is the water content below which the soil behaves as a solid. Having your soil behave as a solid is good. Solids are strong. Even plastics are good. Plastics have a strength. Newtonian fluids are terrible. You do not want them. You do not want your soil behaving that way, because basically they're going to act like water. So let's say you have a soil that has a plastic limit of 30 and a liquid limit of 68. If your water content equals, let's say, 28%, how's your soil going to behave? It's going to behave as a solid. What if it's 37%? Then it's going to behave as a plastic. Still has strength, right? Not as much strength as a solid, but it's still going to have strength. What if it's 80% water? Bad news, right? It's going to be liquid. But let's say now we have a different soil, okay? Let's say now we have a soil that has a plastic limit of 15 and a liquid limit of 32. If it's 28%, how's it going to behave? As a plastic. Still has some strength, okay? Now at 37%, washes away. 60 or 80% washes away. Okay, so this tells you whether your soil is going to have strength at various amounts of water. Okay? So here we go, just another example. Soil 1, plastic limit 28, liquid limit 38. Same thing as the previous example. If your water content is less than the plastic limit, behave as a solid. 28 to 37%, behave as a plastic. Over 37%, it'll behave as though it has no strength at all. This is just going back to thinking about soils according to how we discussed stress and strain rate a couple weeks ago. So here's this XY plot that we used a lot a few weeks ago. So over here on the left we have stress. You could also think of this as slope. The higher your slope, the more stress you have. And then strain rate, how fast it deforms. If you're over here on the left, it deforms slowly. If you're over here on the right, it deforms fast or quickly. Again, how would water and tar plot on this graph? Remember, water requires very little stress to flow very quickly. And tar requires a lot of stress in order to get it to move. And the slopes of these lines are the viscosity. Tar has a high viscosity, water has a low viscosity. So that's stuff that we looked at a couple of weeks ago. And again, both of these go through the origin, right? So these are Newtonian fluids. They don't have any strength at all. The only difference is one is more viscous than the other. They will move. They will both move if they're on any slope at all. The water's just going to move faster. So that's a Newtonian fluid, but remember there's another type of fluid called a Bingham plastic, and Bingham plastics have a minimum amount of stress that you need in order to get them to move, or a minimum amount of slope. You can think of it that way. So the more slope, the faster both move, but the water is always going to move faster than the tar. But the point of this is that they have no strength at all. Any slope and they move. If we go back to our soils, this is how they're going to behave if you exceed the liquid limit. So you can think of it this way. If you have a soil on a low slope and its liquid limit is exceeded, right? It's going to move, but it's not going to move very fast. If it's on a high slope, it's going to move, and it's going to move really fast if you exceed the liquid limit. But in both cases, your soil is going to start moving, which is not really a good situation if you've built something in it. So again, these are called Newtonian fluids. You don't want your soil to act like a Newtonian fluid, because your soil is going to move, and anything you have built in your soil is going to go with it. What you want are soils that have strength. So you want a soil that's either a solid or a Bingham plastic. And Bingham plastics have strength. You can put them on a slope. As long as the slope isn't too high, they're not going to move. At some point, though, your slope might be high enough to get them to move. You have something with a low viscosity, once it starts moving, it moves fast. And that would be what we have here. Other case, you can have something that once it starts moving, it just keeps moving really slow. And that would be higher viscosity. So you want your soils to have a yield strength. They can accommodate some stress from either building stuff on it or being on a slope. All right, let's think about this. What happens as more water is mixed into a thick mud or soil? So let's say this is our behavior profile for a soil. And now we're going to add more water in it. That water is going to get into the spaces between the grains, and it's going to start separating those grains. So there's going to be less touching, right? What does that do to the strength if there's less places touching? So the strength drops, right? If you add more water, what does that do to the viscosity? makes it runnier, right? Lowers the viscosity. So just by adding water, you can take something that behaves like this, and you can reduce the strength and the viscosity. So it will not only move easier, once it moves, it's going to move faster. So thin mud, and if you end up putting enough water in it, it's basically going to end up behaving like water. So this is what's going to happen to your soil as more and more water gets added into it. As soon as you reach a condition where the material has lost all of its strength, that means you've exceeded its liquid limit. As long as it has some strength, you're going to be between the plastic limit and the liquid limit, where it's behaving as a Bingham plastic. So your strength drops as less grains touch. Your viscosity drops as less grains touch. Okay, final variable, something called the plastic index. This is the difference between the liquid limit and plastic limit. Okay, so let's say we have this soil. Soil scientist tests it, finds out that the plastic limit is 28%, liquid limit is 38%. Let's say it has 14% water in it. How will this soil behave? It's under the plastic limit, right? That means it's going to behave as a solid. What if it has 30% water? It's going to be plastic. What if it has 40% water? Be a fluid, right? What's the plastic index for this soil? It's 10. The difference between it, okay? Now let's look at soil 2. Has a really low plastic limit, right? So the water content range where it stays solid is not really big, right? But once you exceed 11%, it's going to behave like a plastic, right? It has some strength. And you can see that it holds some strength all the way up to 74%. It's a much wider range, right? What's the plastic index for soil 2? 74 minus 11 is 63. These are really different, right? 10 versus 63. There's something different about the soil, right, that allows one to accommodate so much water before it loses strength. Well, in order to get a plastic index that's really big, your soil has to be able to absorb a lot of water. But that comes at a price. If it's absorbing a lot of water, that means that your water is holding on to a big volume of, or your soil's holding on to a big volume of water, right? What that does is it makes your soil expand. And then what happens as it dries out? Contracts. Do you want to build into a soil that every time it gets wet and dry, does this? No, these tend to be really clay-rich soils that have a lot of shrink and swell. Now you see our soil 1 has a very small plastic index, right? Those aren't always great either, because what it means is that it can go from solid, that's strong, to a liquid, a fluid without strength, over just a really narrow range of water, okay? It soaks up just 10% water and it completely loses all of its strength. That's not good. Second one's not good either. It still has strength, but it's swelling the whole time. And if you go and look at homes that are built in clay-rich soils, look at the basements, If they're older than 10 years or so, you're going to see all sorts of cracks in the foundation. This stuff is famous for cracking foundations, high plastic index soils. So soil 2, it's going to start losing its strength at a lower water content, but it's going to hold its strength to a much higher water content. But it does so by sucking up that water and expanding. There's a type of clay up in the Dakotas and in Nebraska called bentonite. It's a clay that's made by volcanic ash that turns to clay over time. So 50 million years or so, Yellowstone area, actually here in Colorado, we had lots of volcanic activity that blew massive amounts of ash off onto the prairie. All of that stuff is now turned into this clay called bentonite. And bentonite can expand by 10 times its size. And we use it. We use it to line ponds. We use it as drilling mud. They use it for cat litter because it's so absorptive. So it has a lot of use, but it's terrible to try to build in because these soils just do the yo-yo thing with the expanding and contracting. So for a high plastic index soil, that water is being held in the soil, and since it can accommodate so much, it greatly expands and contracts. So what you really want is kind of something in the middle, not too small and not too big. If it's too small, then it loses its strength too rapidly. If it's too big, then it's highly expansive. So you want sort of an intermediate value for plastic indexes if you're going to build in it. Intermediate, but as high as possible. You want your soil to be able to accommodate as much water as it can before it loses its strength. So you want your soil strong, you don't want your soils to expand and contract, and you don't want your soils to change behavior abruptly by adding just a little more water. So this is kind of how an engineer views soils. Really different than how a farmer would, right? Farmer, they care about, do you have good soil zone development? Do you have good nutrients in your soil? All this is concerned with is my soil strong or is it weak? And how much water can it accommodate? Okay, so here you go. Here are 3 soils. I want you to pick one to build in. You're going to build a 2-story home. Now my class is a bit like the real world, and a lot of times I'll give you 3 terrible options. I don't have 3 terrible options here. I have 1 terrible option and 2 that are okay. Which soil do you definitely not want to build in? Soil 1. And there's 3 reasons why you don't want to build in this. Why? What are the 3 reasons? High plastic, it's the highest plastic index of all of them, 49, right? So it's going to shrink, swell, and crack your basement. What else? It has the lowest liquid limit and the lowest plastic limit. So it changes its behavior at the smallest amount of water of the 3. What else? It's on the slope, right? So, yeah, this one sucks. This is terrible. You don't want that one. Now the next 2 is not so simple, right? Both low slope. We can ignore that. They're going to be equal in that. This soil right here has a nice moderate plastic index, not too high, not too low, and the values are pretty high. Soil 3, the values are higher yet, aren't they? The range is narrow. The plastic limit's only 12. That means it can change from solid to liquid over a very narrow water addition. But the fact that the numbers are pretty high says it's probably a decent soil too. So basically you could pick either one of these and make a good argument for it. You just can't pick one. One's terrible. There's nothing good about soil 1. So those are the things you would look at. You look at the values of the plastic limit and liquid limit. You look at the plastic index and check out the slope. Soil 2 and 3, both pretty decent. Neither one is going to shrink and swell very much. Both have fairly high values. These are fairly high values for soils. And they're on low slopes. All right. Yeah, we don't like one. All right, this is the last thing we'll cover. Sensitivity. There are some soils that are strong unless they are shaken or vibrated. And once you shake them or vibrate them, these soils can lose all of their strength instantly. This tends to be common in soils that are clay-rich. And it can also happen if you have pure sand deposits that have a lot of water in it. Where you have only sand grains, the sand grains are just barely touching, there's water in the pores, and if you shake it, those sand grains don't touch anymore. Quicksand. That is the definition. What are you not supposed to do in quicksand if you want to get out? Move, right? Which I don't know how you get out if you don't move, but that's the dilemma with quicksand. And you can get these vibrations several ways. Digging, blasting, living next to roadways. But probably the biggest is through earthquakes. And there are soils in earthquake country that are just terrible to build in. Because the minute there's an earthquake and the soil starts shaking, they lose all of their strength. And anything that's built in them topples over. Probably the worst example that I've seen of this happened back in the late 1980s. There was an earthquake in the San Francisco area. It happened right during the World Series. Right as the game was about to start, this big magnitude 7+ earthquake hit and shook the whole Bay Area. And there was damage, but the damage was really localized to 2 areas. One was a place called the Marina District. It's a really ritzy area in San Francisco, and it didn't actually used to exist. That was the thing, is that there was a shoreline, and people had built there, but it wasn't real nice homes on the shoreline. It was sort of old buildings from back in the early 1900s. Well, Bay Area has lots of wealthy people who clamor for shoreline. So what they did is they got engineers to fill in the bay with mud. And then they built homes on it. So you have this whole new area that was filled with bay-filled muds, and they put all these beautiful homes on it. Well, as it turns out, the bay-filled mud was really rich in clay, and the soils were highly sensitive. So when the earthquake happened, all the homes that were built on the clay collapsed instantly. I was there like 2 weeks after this, and you could walk and literally draw a line on the ground where they had put the mud, because on one side of the street, you'd have a perfectly beautiful old home, and on a new side of the street, you'd have this huge, monstrous, rich home that just totally destroyed. The other place where they did this was, if you've been to the Bay Area, you know there's some big bridges. You've all seen the Golden Gate Bridge? Well, there's another one that leads from San Francisco to Oakland called the Bay Bridge. And when you build a bridge, you got to put pilings in. And they built up areas with mud to put these support structures in. Well, the minute the earthquake happened, the support structures failed. And this was a double-decker highway, and it collapsed on top of one another. And I don't know if I have photos or not. So there's the Marina District. You see in the background those nice, perfectly fine-looking homes, and then you see these ones that are toppled. All the ones that were toppled were on this bay mud with highly sensitive soils. And then about a mile-long section of the freeway collapsed. This is where most of the deaths occurred, unfortunately. All of the places that collapsed, the support structures, which are right here, were placed in this highly sensitive mud. So it was strong until you shook it. And then it had no strength at all, and it would buckle and collapse. So these are a real point of interest for engineers. And I think we will stop there.